Hello, everyone, and welcome to the VaNTAGe seminar. Today, we're continuing our series on profinite groups and Galois theory, and we're very happy to have Chris Hall, who will be talking about division fields of superelliptic Jacobians. And Chris, is
Okay.
it all right if we record this talk?
Yes, it is. Thank you.
Wonderful, and please feel free to ask questions throughout. Okay, Chris, go ahead.
Okay. Thank you very much. I want to repeat a thank you to the organizers for an invitation to speak here. This is definitely a topic, I think the theme, Galois theory, et cetera, is certainly something I like to talk a lot about. And this is a project that I'll say it's a bit older. There's nothing terribly fancy and new within this, but it's never been properly written out, let alone discussed. And I thought this was an excellent opportunity to bring the project to the public. So, I'll get started here. I am going to first lay out some data, some basic data that we're going to use throughout the entire talk. And I'm going to try to do my best to at least keep some of the data sort of low tech. So, if you're hoping to hear a talk about stacks or something like that, you may want to move on. Instead, I'm going to sort of start with the language of varieties. And as such, I'm just going to fix an algebraically closed field K. I need a name for the characteristic, so we'll call it P. I'm also going to fix a positive integer m, and then a function field. And you do want to note that this is a function field in m+1 variables. There is a reason for numbering things in this way that will become clear as we move on. So that's some of the data. Some other data I need. I need an auxiliary prime r. This is really intended to be fixed throughout the duration of the talk, though you could certainly ask what happens if it varies. Once I fix that prime r, I also want to make note of the fact that r is invertible in my field K, so I've got the cyclic group of rth roots of unity contained inside. This is both in the ground scalar field K and in the function field capital K. And then I'm going to fix some exponents. And you'll see why I call them exponents in a moment. What I really want to sort of highlight for you is that they're somewhere strictly between 0 and r. And since r is prime, this means they're coprime to r. And then there's some other second thing that sort of stays hidden for a little while. I'll show you where it comes out later on. But all I'm really going to do is add up those extra integers. There's some little negative sign comes up later on. But the main thing I do want to do is sneak in an assumption, which is that E infinity is actually coprime to R. So that's tiny. Otherwise, with that data fixed, we've got what we need to introduce some geometry. So the first thing I'm going to do is introduce this this affine curve. It really has a different name, not hyperelliptic. And it's a very nice form, right? It's y to the r equals, and then some polynomial in x. And you can see, of course, that the EIs are actually appearing as exponents as I claimed they would. I also want to take and think about the smooth completion of this affine curve. This is a well-defined thing, unique up to isomorphism. I don't want to go into details of how it's defined. It's a fairly basic thing within the context of the talk. It's a really nice object. We'll talk a bit more about its geometry in a little bit. I will say now we can talk a little terminology. And so it's common when you're thinking about the case r equals 2, so you have y squared equals a polynomial in x, that you'll refer either to an elliptic curve or a hyperelliptic curve. And it's essentially a function of the genus of the curve. We'll come back to that in a bit. Specifically, elliptic means genus 1, hyperelliptic means larger genus. So these are very traditional and standard terms. I'd say less standard, but important for this talk, is the term of a superelliptic curve. And this means that my curve has an affine form in this shape, where now that exponent r is at least 2. These are not exclusive. There are elliptic curves which are superelliptic curves. There are hyperelliptic curves which are superelliptic curves. So minor point, but just something to keep in mind. And the last piece of data for now is I want to think about the function fields of these curves. They have the same function field. This is in some ways how you define C, is in terms of the function field of U. And concretely, this function field, really it has two variables, x and y. Okay. And of course, there's a relationship between x and y, which is exactly what the affine form expresses. All right, so here's our data. We've got a function field we're working over. We've got some superelliptic curve, an affine model we're working with, and we're going to think about its function field. So I'll remind you, yeah, this is our affine curve, and I want to just give you some facts about this curve and really the function fields as well. So for example, this function field of u, which is also the function field of c, is actually a Galois extension of k of x. And it's a nice Galois extension. It's cyclic, abelian, right? Well, abelians obviously if you're cyclic, but it's got a nice mu r group. Okay, so those are our roots of unity. Then, and this just comes from the fact that we're adjoining y, and y to some power, or well, y to the r specifically, is, this form in x. Now, that Galois action on the function field extension, so k of c over k of x, actually gives you an action of Galois, this mu r, on the curve c itself. And in particular, if you look at the orbits of that action of mu r, those are exactly the fibers of the function from the smooth complete curve to the projective line, which comes from the element x of your function field. Okay? Every element of the function field can be thought of as a function from C to P1. X, or taking the x coordinates, say, of an affine point, is one such function. Okay, those are basic. I'm not going to say anything more about them. I will say something a little more, though, which is specifically about this map from C to P1. So it's an R-to-1 map in general, but it does have ramification. And specifically, it's ramified over these points. Okay, so over the t's, i's, and over infinity. And the ramification is really coming from the linear form x minus ti that you see in the form of the curve. And I can also tell you that this map will be unramified everywhere else. Okay, now this is a fact I'm going to go ahead and actually explain, because the proof, we'll see something like it come up again later on, and it would be nice if you could walk away from the talk having understood at least one thing. And so the proof is fairly straightforward. Again, I'm trying to analyze really how this Galois extension ramifies. I've phrased it here in terms of the map, but as a Galois extension, you might really think of the affine curve, the model that we use to define C to begin with. And if you look at that model and you pay attention to it, then what you see is that when you think about what happens at x equals ti, then your model ends up having some nice shape. Okay, so if you think of the x minus ti as a uniformizer on the projective line, then you could actually say, great, the form of this equation looks like a unit times a uniformizer to an ei'th power. And remember, by hypothesis, ei was co-prime to r. And so because r is prime and we have this coprimality, it's a really easy analysis to say, aha, this is a totally ramified place that is x equals ti. And if you look at the projective closure of u and P2, and you look at a model around x equals infinity, then you get a similar kind of equation, unit times uniformizer to the e infinity instead of ei. And that's also co-prime to r. And that, I remind you, is the hypothesis I slipped in on the first page, this hypothesis of coprimality. Now, these two lines, so they encompass all the ramification. If you look at any other value of x, so basically x not equal to some ti, and you plug it into the right-hand side, you get a unit out. And so you're just looking at a good old Kummer extension, y to the r equals a unit. That's really easy to understand as being totally unramified. So we have this nice thing, and in fact, we have a really nice picture that we can use to summarize the situation. Before going further, I want to credit help with a real intelligence, Hyung-Jung Kim, to prepare this diagram. Wouldn't have been able to do it on my own. I'm not sure how I would have asked an AI to do it either. Anyway, the picture I will stress for you is right now just the particular case of r is equal to 3, but what you can see is I've got 3 sheets upstairs and then several points of ramification labeled, okay? And those are all the different TIs and our point infinity. So this is what our picture looks like. I mean, this is what the curve looks like. This is what the map to P1 looks like. And now I'll tell you something nice and easy about this curve using the ramification information. I'm going to tell you what the genus of the curve is. You can see the formula on the board. I will remark before diving in any further, you can already begin to appreciate a little bit why I numbered things the way I did, in particular starting with 0, because that meant I had an m here instead of, say, m minus 1 or something like that. All right. Um, Proof, it's not going to surprise you a whole heck of a lot. The really essential point here is that the map from C to P1 is tamely ramified and has degree R. And in particular, well, it's also Galois, and R is invertible in our ground field. So we can apply the Riemann-Hurwitz formula. And if you do apply the Riemann-Hurwitz formula, you get your normal expression for really Euler characteristics, I would say, left and right-hand side. And some relationship between them. The thing that you'll sort of easily observe is we have the contribution coming from ramification from the m plus 1 t's and the point at infinity, and then the rest of the formula is what it is. And it's really easy algebra, of course, to rearrange it and solve and see you get this value for your genus. Okay. All right, so I'm just going to call my genus G. We have a nice numerical value for it, but it's just much easier to call it G. And I'm going to start thinking some more geometry here. Okay, so in particular, I want to think about the Jacobian of C. I remind you, this is a G-dimensional abelian variety. It's even a principally polarized abelian variety. And I'll make use of that particular point in just a moment. I'm going to introduce a new prime. This I'll call L. I prefer that it be invertible in my ground field. It's easier to avoid 2. And for reasons I could get into perhaps later, taking L equals R is not quite so interesting for superelliptic curves, much in the same way that 2 torsion for Jacobians of hyperelliptic curves is also less interesting than any other torsion. So I'm going to impose these hypotheses on my prime L and just sort of carry them through the talk. Now that I have a prime, though, I can focus in particular on the group of L torsion for my Jacobian. I'll remind you, because the Jacobian is G-dimensional and because L is invertible in my ground field, this is a 2G-dimensional FL vector space. So something nice and easy, sort of in particular finite in nature. And then because my Jacobian is principally polarized, it has a VaE pairing. Well, it really, it has an isogeny or even to its dual, or it's isomorphic to its dual, I guess I should really say. And this induces a nice pairing on torsion, which we call the VaE pairing. I won't define it for you. I imagine you've seen it before. I'll just remind you that its important point is that it's FL bilinear and alternating, and well, maybe I should also say non-degenerate. Okay, so it's a very nice extra piece of data that one can attach to the L torsion. All right, so this is usual stuff. And once I have my L torsion, there's really sort of 2 groups that are interesting to think about. One of which is just the group of linear automorphisms. And so this is going to look something like a GLN for some n. Sitting inside of that group of linear automorphisms, though, I have automorphisms which respect the VaE pairing. They're isometries, I would call them, with respect to the pairing. And so those are, some subset of elements that are even really subgroup of elements that we prefer to focus on. And the reason will become clear in just a moment. I need a little bit more data, though. I'm going to introduce my L division field. So these are some of the division fields I'm referring to in the title of the talk. And I will tell you that a lot of the hypotheses we've made, like on L being invertible, et cetera, means that this is a nice extension of K. It's a finite Galois extension. And that means, of course, we can talk about its Galois group. And I'll just sort of say, and then sweep the details under the rug, that it's a basic fact that the Galois group of that field will always respect the VaE pairing. And so your Galois group in particular can be really regarded as a subgroup of this group of isometries, of this symplectic group. All right, now for those in the know who are used to seeing abelian varieties, VaE pairings, and the like, they may also remember that, well, the VaE pairing, of course, takes values in L roots of unity. Remember, in our situation, the L roots of unity already exists downstairs. So there is no Galois, or at least non-trivial Galois action on L roots of unity. And that's why we're looking at genuine symplectic isometries and not something more generic like a GSP there. Okay, so that's a minor point. The big point here, though, really is that we can regard the Galois group as some subgroup of a group of isometries. Okay, and so now the question that drives me and really I would say underlies this talk is, well, how do these groups GL vary with L? And well, you might even say with R and M. I mean, to me, R and M are fairly fixed for the talk, and then L varies, but of course you could really take different R's and M's as well. Okay, now we've got our division fields, we've got our superelliptic curves, we've got our Jacobians, and so now we really have all the ingredients of trying, the talk itself, I guess that's it. Okay, so I want to start off by thinking about telling you what is known, okay? And for the moment, and just on this slide only, I'm going to focus on the hyperelliptic case, well, elliptic hyperelliptic case. So specifically, I want to think about R is equal to 2. And I'll remind you, L is not 2, it's also not R, but same thing, and it's not equal to P, okay? And I'll tell you a fact that was proven independently 3 times. And that is that the Galois group, which a priori was just a subgroup of this symplectic group, is in fact equal to that symplectic group. So you get the upper bound is actually the proper bound, so to speak. It's also a lower bound. And so the history of this is interesting. Jukeng Yu proved it first. His manuscript, though, remains unpublished. It was something that was shared. Certainly, I know Jeff and Rachel had access to it. I had access to it. We were aware of his result. Independently, though, Jeff and Rachel came to their own proof of the result, a very elegant argument using an inductive argument. And then I, on my own, proved the result as well. And our techniques are different. In fact, what I'm going to do is really sketch for you the proof as I would think about it, partly because it's illustrative of what we're going to be doing a little bit down the road here. So the way that I like to prove the theorem is really to think about a couple of facts, one of which is to do some analysis of this Galois module. And I'll tell you one basic fact about it, which is that it's actually a simple module. Now, recall that means that the only Galois invariant submodules are the whole space itself, the whole module, and the zero submodule. Okay, so I'm telling you in particular, this thing is essentially irreducible. Think analogous to telling you some polynomial is irreducible. A deeper fact is that I can tell you the Galois group is generated by a bunch of special elements called transvections. And I've given a technical definition of a transvection here. It's unipotent. The fact that, the rank of t minus 1 is 1, this tells you it fixes a hyperplane. So it almost fixes the entire space. Really, it's a codimension 1 subspace that it does act trivially on. And then, as I repeat, the fact that that thing is actually unipotent. So if you were thinking in terms of Jordan blocks, you have a whole bunch of blocks of size 1 and then a single block of size 2. That's what such a transvection looks like. Okay. And if we take this as a fact, that we understand the module is simple, we understand that it's generated by transvections, and moreover, we remember the fact that GL is contained inside the symplectic group, then we can apply a theorem of Zaleski and Serezhkin to conclude that actually we must contain the symplectic group as well. Okay, so on the previous slide, we had an upper bound. This inclusion went the other way. Now we're giving a lower bound, and in particular, we're really saying, yes, these two groups are the same, just as was claimed in the theorem. Before moving on and talking about more general results, I will just say it's really worthwhile to compare this result to a more basic theorem in group theory, one that would come up if you were studying, say, Galois groups of just monic polynomials. And so in particular, if you know you're looking at the Galois group of a monic of degree n, you know your Galois group is a subgroup of Sn. There are very few, there are many irreducible subgroups of Sn, but there's exactly one that's generated by 2 cycles, and that's the group Sn itself. And so this is a fact in group theory. If you have, irreducible subgroup of Sn generated by certain special elements, then you'll be looking at all of Sn. What we did for this symplectic theorem was to say, great, we have something irreducible, really simple, generated by a bunch of simple elements. Those are transvections. And as a result, we must be looking at the entire group. So that's the flavor of at least the proof that I took. Okay. All right. But I want to move past the hyperelliptic case because that is an old theorem. It is something that, like Jeff and Rachel's paper, my own, go back good 15 or 20 years at this point. And what I want to do next is sort of move beyond, and instead of talking about the hyperelliptic, talk about the actual superelliptic stuff. And so I'm going to remind you that we had several slides ago a discussion about the fact that this group mu r acted on the curve C. And then J is the Jacobian of this curve. And I'm going to tell you that I've just claimed that there's a nice canonical action of the R roots of unity on J, and consequently on the submodule of L torsion. These are relatively basic facts, nothing deep hiding here. There's a slightly stranger fact, though, which is something I would regard this as a statement about how the Weil pairing and the action of mu r interact with each other. And I think it's most easily expressed as just a statement about, two particular Weil pairings being equal to each other. I would draw your attention to the fact that when you're used to sort of usual moving scalars around and say a Weil pairing, you'd probably expect this zeta inverse to be a zeta. But it really should be a zeta inverse, and I want to point that out because you really should be thinking of zeta inverse as maybe zeta bar, a complex conjugate, and you should really be thinking unitary thoughts. Having said that, I'm going to focus now on the isometries of the Weil pairing, which commute with the action of mu r. So that's what I'm calling the centralizer. Okay, and my claim is that, well, all right, first I'm just going to define the group as the centralizer. And I'll say that, well, okay, if r is equal to 2, this is the same group that we had before. We didn't gain anything new in this situation. It's when r is really 3 or larger that this is really a proper subgroup of the symplectic group and represents something new and interesting. And the fact is, new or not, the Galois action on L torsion commutes with the action of mu r. And the reason for that is the action of mu r is defined downstairs before you even make any Galois extensions. So any action defined downstairs has to commute with Galois in that regard. So a basic fact is great. We've, even further narrowed down to what kind of envelope our Galois group can lie inside. And in this case, it's this group called gamma L. Gamma L is nice. It's a little ambitious to actually ask for equality in this proposition. And it's a little bit better to focus on really the derived subgroup of gamma L. Generally, this derived subgroup will look like a product of special linear or unitary groups. And strictly speaking, that statement's only correct if I say R is odd. For R equals 2, you just get back the symplectic group. There's nothing new there. But as soon as R is 3 or larger, gamma L itself is sort of a unitary group, and then this derived subgroup is a special unitary group or a special linear. It depends. Okay. And so this derived group, though, it is what it is. And now having introduced it, I can state a theorem for you. So Jeff and Rachel, when they proved Jukang's theorem, they also proved a result for trigonal curves or superelliptic curves where r is equal to 3. And specifically what they showed, at least the way I will phrase it, is that they showed that this Galois group GL is big. Now, what I mean by that is that it contains that derived subgroup. This is my technical definition for a big Galois group, or I would really say a big subgroup of gamma L. And so what they show is something slightly different, but it can be interpreted as saying it this way. And in particular, what they're showing is that really you get a big Galois group as long as M is at least 3 and R is equal to 3. And then all L is exactly sort of the things that we've already been excluding, things like 2 and R. Okay. So this is a really nice theorem. Uh, it inspired me to think a lot more about this problem, and that's really the basis for this project in this talk, and that's to prove a theorem that tries to deal with general R. So now what I'm claiming for you is that, yes, this group GL is big, almost always. Here are, the conditions you need. I too need M to be at least 3. I'm also allowing R to be arbitrary now. It's still prime, recall, an odd prime, but otherwise arbitrary. And okay, I'm going to throw away L equals 3 as well because it can be a bit of a painful prime as well when it comes to some of these group theory things. So just to be safe, I'm excluding it and saying, great, for these R's, M's, and L's, I can tell you my Galois group is big. And not only that, I can even tell you exactly sort of how much it sticks out. I can look at the quotient by the derived subgroup, and I will tell you that you get a mu R. Okay. So this is a statement about these division fields of these superelliptic Jacobians. The only conditions I've really have placed for you are on the M and the R. M needs to be a minimal amount. And once I know these things are true, I will tell you that, in fact, we're always getting big Galois groups. Okay, so the rest of the talk, what I hope to do is try to give you a bit of an explanation or some understanding about where this comes from. So, all right, the first thing I want to do is just before diving ahead is remind you of, the most basic statement we have at the top of this slide, which is the fact that I have an action of mu r on J, the L torsion, okay? And not only that, it's a faithful action. So there's something interesting that's going on. And I want to tell you more about the module structure as a result. To do that, I'm going to just introduce some extra data. What I want to do first is to look at the group ring FL bracket mu r. So really, remember, my coefficients are finite field coefficients. They live in FL, okay? And then, but you could think of this group ring as being an R-dimensional F vector space, if you like, freely spanned by mu r, the elements of mu r. One particular point I will really emphasize for you here is that this is a semi-simple algebra, okay? In particular, when I try to think about linear representations of mu r over FL, then I will always get a semi-simple representation. I can decompose it into simple submodules as a result, or a direct sum of simple submodules. And this owes to the fact that R and L are distinct. Okay, so this is one of the big reasons I really want L to be distinct from R. L equals R requires a different kind of analysis. Okay, but putting that aside, I'm going to create a mu r module for you. I'm going to do so by highlighting the ring of integers in the cyclotomic field Q adjoin mu r. Now, this is just a field. This is the degree r minus 1 over Q, Galois. The Galois group is the automorphism group of mu r. Wonderful extension. And I didn't say, Z bracket mu r for its ring of integers because I don't want to conflate that with the group ring. We'll just call this ring R. Okay. And what I'm going to do with that ring is I'm going to look at its reduction mod L. So I can look at the principal ideal generated by L in particular, quotient out by it. I get some sort of a ring. But not only is it a ring, it's even a mu r module as well, because in the ring of integers R, I have multiplication. In particular, I can multiply by R roots of unity and get back something in the ring. And the same thing is true in the quotient ring as well. So this is a really nice ring. It's also a nice module. And in fact, what I will tell you is that the L torsion module of my superelliptic curve is isomorphic to M copies of this quotient ring. Now, as a module, okay, I'm not picking up extra ring structure when I write down this quotient. I'm just telling you that as mu r modules, these two modules are isomorphic to each other. Okay? And again, a second time, we sort of see there's a method to the numbering here, which is, I chose to start from 0 because I get a nice simple integer in my exponent. All right, so let me tell you about how this proof works. Okay. This is something I also want to write out a little bit, and now this will actually connect a little bit with what we did before. So the idea is I'm going to exploit the fact that this is a semi-simple ring, and it will suffice to show that the module on the left-hand side and the module on the right-hand side both have the same characters. So I'm going to write down some characters for myself. So one character I'm going to look at is just the character of the entire group ring itself. And it's easy to determine its values. It's R at the identity element, 0 everywhere else. I'm not going to write that down on the board for you. What I will tell you is that if I take that character and subtract 1, then I'm going to be getting the character of my R sub L. Okay. Now, the difference between, this FL mu R and then the R sub L is basically we have gotten rid of the one-dimensional space of invariance inside of the group ring. And so that's why we're subtracting off a 1, I claim, when we try to write down the character. So this is what it is, but the point is I have told you what the character of RL looks like. So M times that will be the character of the right-hand side here. On the other hand, I can also ask what's the character of J bracket L itself. This is the thing I sort of really am interested in. And what I will tell you is that we can, again, apply some sort of Riemann-Hurwitz formula. But now this is an equivariant Riemann-Hurwitz formula. What it's going to give us is a formula relating this character psi L with several other characters. But the formula is going to look a lot like what we had before. Okay, we've got what would have been twice the genus upstairs, minus 2, degree, twice the genus downstairs, minus 2, and then ramification contributions, something minus 1. Previously, it was R minus 1, but it is what it is. And so, you simplify the right-hand side, and then you end up getting the nice relationship that you want between psi L and this other character. And in particular, this is really the idea. This is the main point, that these two modules actually have the same characters. I'll throw in a small parenthetical remark here, which is that if you take this psi L and you evaluate it at 1, then, well, that's the same as evaluating this character at 1. You get back the genus formula that we had before for our superelliptic curve. Okay, and this isn't an accident. This is sort of a normal output, I guess I would say, of equivariant Riemann-Hurwitz, is that looking at what the character does at 1, or the identity element, will always tell you what the genus is. Okay, so we actually can understand this module as a mu-R module, and in particular, it looks like several copies of a fairly nice module, right? This ring, what looks like a quotient ring here. Okay, so so far, we've talked division fields. These are L division fields. This was obtained by adjoining all the L torsion of my Jacobian. I want to be a little less ambitious now, because I'm also going to try to take my group action into account. To explain this, I'm going to need to pick some data. So I've got remember, this is my cyclotomic ring of integers, and I can talk about the primes in the ring lying over L. So pick your favorite. You can call it lambda. It's an ideal. So, but it's even, you could say it's a mu-R submodule, because it's closed under action with respect to mu-R. So, okay. We can also now look at the residue field, R mod lambda R. Okay. And this, I do stress, is a field precisely because lambda is a maximal ideal, inside of R. And so it's some finite extension of FL in particular. Okay. Now, the action of mu-R on R induces an action on the quotient. And so we can really say, great, this is a mu-R module. And because this module is annihilated by L, it's even an FL mu-R module. Okay, so I would have you look at this module F lambda with sort of two eyes. One is an eye that thinking of it as a field, a ring, a really nice place to do some linear algebra. And on the other side is as some particular FL of mu r module. Okay. All right. Now, having identified my L, or my lambda, excuse me, I want to talk about the module of L torsion, which is annihilated by lambda. So these are the elements of torsion for which every element of lambda annihilates that torsion element. Okay. And I will tell you some nice basic algebraic facts about these rings and modules. So for example, if you look at the RL, so remember this is ring of integers modulo L, I can actually write it down as a product of all the different residue fields. This uses the fact that R and L are distinct. Okay, wouldn't be true if R was equal to L. So I can certainly write this ring R mod L as a product of fields. That's nice. It's also, as I said, though, those fields should be thought of as modules, and so you should also think of this as an identification of modules. Okay, so that's a nice basic fact. That was just about the, sort of mu-L modules themselves as abstract things. Now I want to tell you specifically, about my torsion. And the most basic point is that the torsion decomposes as into the different lambda submodules. Those are, lambda torsion submodules, I should say. So that's a fairly nice thing. And moreover, I can then tell you what each one of those lambda torsion modules looks like. Specifically, I can tell you it looks like several copies of this residue field F lambda. Now, that second statement also you can start to see that, okay, this thing looks like a vector space over F lambda, and it even looks like an M-dimensional vector space over F lambda. And that will be useful for us. All right, so what I want to do is I'm going to go ahead and focus on FL lambda automorphisms of that space, okay, linear automorphisms. And that's what I will refer to when I say GL of J lambda is that group. Concretely, you pick a basis. Because it's an M-dimensional F lambda vector space, you'll be isomorphic to GLM of F lambda. All right, now, this is a piece of my L torsion, my J lambda is. So I can always focus on that piece and the division field that it generates. And I will tell you that a priori, it could be just sort of an arbitrary extension. It is, in fact, separable. It's even contained in our Galois extension, KL over K. And that's not a hard thing to see. Because it's contained in that Galois extension itself is separable, but it's even normal over K itself. So it really is a nice Galois subextension. And so let's write down the Galois group. And my claim is that I know I can regard it as a subgroup of FL linear automorphisms. And really, I've just unpacked for you, or maybe repackaged, the statement that Galois commutes with the action of mu r. And remember that the action of mu r, the module structure, that's really sort of how we even honed in on J lambda to begin with. It's thinking about how our RL decomposes, thinking about how JL decomposes, etc. So my Galois group is what it is. It's a subgroup of this general linear group. It's also, by virtue of being a Galois group of a Galois subextension, or of this Galois field KL over K, the Galois group is even a quotient of the bigger Galois group. So the small Galois group is a quotient of the big. And a nice, easy thing about linear algebra, Galois theory, and really, this decomposition of our L torsion module is that if we look at all the different K lambdas and we take their compositum, then we are going to get the extension KL. And as a consequence, when we think about the Galois group of KL, we can really see it as sitting inside a product of the Galois groups of the K lambdas. And so, we certainly have the product of the K lambdas, and I say that it's a subdirect product to mean that it is some subgroup which maps onto each G sub lambda. So for each natural projection, the subgroup maps surjectively onto the codomain of the projection. So this is a standard fact in Galois theory. Okay, so I've got my lambda torsion. And so now I'm looking at really a smaller extension, which is this KL, and I'm really trying to understand what the Galois group G lambda is of that extension K sub lambda. All right, so now we'll go back and start to talk some unitary things again. To make life easy for myself, I'm going to impose some hypotheses for this slide. I want to focus on m being bigger than 2. We'll see where that comes in later. I want r bigger than 2 because we've already discussed r equals 2 and know what's happening there. And I also want L to be bigger than 3 because, as I said, well, L equals 3 can sometimes be a little bit painful. So I'm just going to ignore it. All right. Now I'll tell you some more facts. So one of which is this J lambda. It's a simple module again. Before I had told you JL, at least in the symplectic case, the hyperelliptic case, was a simple GL module. Now I'm telling you J lambda is a simple G lambda module. I'm also telling you more. I'm telling you it's even a primitive module. Basically that it doesn't look like it's a module, induced from some subgroup of G lambda. And I don't want to get into the technical definition of that anymore, but it's a fairly basic property to ask for a module to have. It's also an important property for us to prove. I need this extra condition. That's why I'm putting it in. Having it, though, I have what is a nice module with some nice properties. I also know that I can pick generators of this module that have a very specific shape. In the symplectic case, they were transvections. Now they're called pseudo-reflections. Very similar flavor. They still have this property that they fix a hyperplane of codimension 1. Okay? But I'm no longer forcing them to be unipotent. The one additional eigenvalue that we haven't accounted for yet, which equals the determinant of the matrix, could be anything. And we'll see more strongly what it actually is. And if I regard this G lambda as a subgroup of, remember, this GLJ lambda, I can talk about the determinant of matrices in that group, and I'll tell you that G lambda, I can tell you exactly what the determinant outputs, okay? We will get this group of R roots of unity. And we saw this group of R roots of unity earlier when I made some statement about the determinant of GL was being equal to mu R. It's really coming in part from this statement here. Okay, now I need one small little piece of notation, which is, I've got my prime lambda. I've also got a complex conjugate prime. And this is really, I'm thinking about Q adjoin mu R as a Galois extension of Q. I have a well-defined automorphism, which is complex conjugation. Concretely, it's take any root of R through to unity zeta to zeta inverse. Okay, and then, do that for everything in the ring. So I have my complex conjugate prime, and having identified it, I can now give you some precise information about these derived groups G lambda. So, all right, the derived group I introduced earlier technically was the derived subgroup of a unitary group, the gamma L. The derived subgroup, of course, makes sense for any group. I can speak of the derived subgroup of G lambda in particular, and I will tell you that exactly what G lambda is, or what its derived subgroup is. I will tell you that it's either a unitary group, that happens when lambda equals lambda bar, or you're some special linear group. Okay. So earlier I said that the derived subgroup of gamma L looked like a product of special linear and special unitaries, and these are the special linears and special unitaries that I have in mind. Okay. Now this statement here, this corollary, this is group theory. Wagner's theorem is really old, like over 100 years potentially at this point. I'm not sure. I'm not sure, but it's old. And nonetheless, it's really a consequence of these few statements that I've made up here, all which are facts about the Galois module. Simple, primitive, the Galois group is generated by these pseudo-reflections, and there's at least one pseudo-reflection of order R. That's the other important thing. So once you combine all these things, it's a group theory result that you're going to get what you want for G lambda. And then additional group theoretic argument, now using sort of what sometimes we call Gorshaw-Ribbit. I think it's Gorsaw's lemma, and then Ribbit enhanced it to really be able to show that this subdirect product of GL that I said GL was before is actually sort of really as big as possible. Okay, and as big as possible means that it contains that derived subgroup D of gamma L. So what we have now on the screen is a first proof. I mean, I still haven't told you how to prove this theorem, but this is the main ingredients of how it is that we prove, the big monodromy theorem for these superelliptic curves and L division fields of their Jacobians. Now, I want to, in the time remaining, try to tell you a little bit more about how I actually even prove this theorem, okay? Because I've made a statement in Galois theory. The easiest Galois theory problem one could have would be to give someone an explicit polynomial and say, is this thing Galois or not? And you can look at the polynomial, you can do as much analysis as you want. You can show it's irreducible, maybe you can study ramification, etc. In my problem here, I don't have an explicit polynomial. I don't have division polynomials. I do not know how to write down these extensions KL or K lambda explicitly. I do know how to describe the Galois groups and generators of the Galois groups, but that really comes from a different direction than some explicit analysis of a polynomial. All right, so let's try to talk a little bit about how it works. What I'm going to do now is introduce some more geometry. And so remember, at the beginning of the talk, we focused on this affine space, M+1 space, because we thought about its function field. And everything we've been doing is over the function field of this variety. And now I'm going to really start thinking more about the variety itself. And in particular, I'm going to focus on the subset of things where two or more coordinates coincide. Okay, so sometimes this is called the thick diagonal, as opposed to the real diagonal, which we mean all the coordinates are equal to each other. So it's a divisor. It's a really nice Zariski closed subset of the affine space. Its complement is open, Zariski dense in the affine space, and it's really this open complement that we're going to focus our attention on. And I'm going to take the curve that was, originally a superelliptic curve defined over a function field, the function field of this affine space, and I'm going to spread it out. And I'm going to spread it out in an obvious naive way, and I'm going to end up with a nice, proper, smooth curve defined over this base B. So this is really a family of proper, smooth curves. For that family of curves, I can talk about their Jacobians, and that forms a family of abelian varieties. You could also think of that abelian variety or family as the Néron model of the Jacobian. And some really nice things are true, like the action of the roots of unity on the curve and the Jacobian. They spread out and they give actions even on this family of curves and this family of abelian varieties. And if I look at J over B, this is a group scheme. I can talk about subgroup schemes such as the L torsion and the lambda torsion in the same way that we did generically. We're just doing it over a base now. And while a priori these are sort of finite group schemes over B, but in fact you can regard them as least sheaves, I claim. Okay? And so these are, I'm just going to say that regard them as least sheaves and say, okay, now this is really sort of the sheaf manifestation of the problem from before. And so, all right, let's try to unwind these sheaves a little bit. So I'm going to fix a base point, and I'm going to go ahead and focus on my ATOL fundamental group. And I'm going to use the sort of normal correspondence between representations of pi1 and leaf sheaves on B to say that these two leaf sheaves correspond to representations of pi1. And in particular, the GL and the G sub lambda are both quotients of pi1. Okay. All right, so that was just topology. I've got a big family, an M+1 dimensional family of curves, but I'm going to shrink it down a bit. I'm going to work down to a one parameter family. So I'll really just go ahead and forget the first coordinate T naught, and I'll look at the fiber of that projection. You should think of the fiber as really you've taken P1 and you've subtracted B1 to Bm and infinity as well. And I'm going to take my curves that lived over the base, my family of curves, and I'm going to look at the restriction to a family of curves over T. This is a nice one parameter family of curves. And I'm going to tell you that this family, if you look at the generic fiber, it has a really nice, easy shape. Okay, mainly what's happened is what was Ti before has become Bi, except in the case of I equals 0, where we got T instead. And by virtue of having a map from T to B, I've got a morphism functorially of fundamental groups. And in particular, I can compose this morphism with the homomorphism from pi1 to g lambda, the quotient that we talked about before. And I can look at the image of pi1 inside, pi1 of t in particular. And all right, there's some extra character I have to introduce here. It's a technical thing. I mean, really, I'll just write it down as it is, but try to tell you instead, how I'm going to use it. And what I'm going to claim for you is that this sheaf J lambda that we wrote down before can really be thought about using what looks like a Kummer sheaf, okay? To sort of properly define the Kummer sheaf in the way I want it, I do need this character chi. I would need what would normally be called an L sub chi, but then I also sort of have to think in the same way as I did before, pay attention to mu r actions, etc. So I'm waving my hands a lot here, but I want to convey that this is a fairly concise statement of a straightforward point. And the upshot of it is this is precisely the statement that allows me to analyze the the inertia and the generators of my monodromy group. In particular, it's analyzing it as a mental convolution that I'm able to show that the thing is simple and primitive. And I can even show that it's big as soon as, well, all right, there's this tiny hypothesis that I don't want E0 and E1 to add up to R. I claim I can make this happen by permuting the EIs, provided that M is at least 2. Okay? All right, so this is the big picture that I wanted to tell you about. So, we introduced these superelliptic curves. We introduced their Jacobians, the division fields of the Jacobians, and then asked the question of what kind of Galois groups do we get? And the answer is that we get big Galois groups. Why? Well, because if you look at a very nicely chosen one parameter family, then already in that situation, we get nice big Galois groups. Okay. I will quickly close here with just to answer one question, which is why, M equals 3 or larger was a big thing in the theorem we did. What about smaller m? And I will tell you already that if we take m equals 2, we can find cases where we do not have big monodrome. And so the specific example that I would have you think about is the super Legendre curve written here. This is a curve that Rachel and I and 6 other people studied together in a nice AMS volume. And one of the things we did in studying this curve was to show that actually this thing has extra automorphisms. Not necessarily downstairs, you have to make an extension. But once you have those extra automorphisms, in fact, this Jacobian is no longer simple. It's actually a square of an abelian variety. And that, the extra automorphism slash this extra structure means Galois group is really going to be smaller than you would expect. And so it's really not big in that situation. So the upshot of this slide here is really m bigger than or equal to 3 is very important. There really is something that goes wrong for m equals 2. And I think I believe it there. Thank you.
Thank you, Chris. Would anyone like to ask a question? Felix, do you want to read your question yourself, or do you want me to read it?
Okay, I can read it. Hi, Chris. So in your theorems, are you able to handle the cases L equals 3 and 2? Or else can you say something about what happens there?
I mean, so L equals 2 is just sort of often creates exceptional behavior. So if you were to look at something like Wagner's theorem and maybe even Zaleski and Sereshkin, that you would find just perhaps some more possibilities for what could happen in that situation. I haven't thought super carefully right now to see if, which of those things could be ruled out or not. My feeling is there's probably situations that can be handled easily, and that if there are situations where there's room for more than one answer, then maybe one of those, some of those unlikely answers actually occur. I don't really know. But to me, it's the kind of thing where the group theory does have sort of small extra exceptions for L equals 2 and 3 that require a little extra work, but I wouldn't say that there's anything necessarily deep or profound about those primes. I'm just lazy.
Okay, thank you.
I had a question. I wondered whether your techniques might also work for dihedral extensions.
That's a good question. I'd have to think about it a bit. I know certainly that one important thing in what I was doing, which was in this reduction to the one parameter family, was thinking very carefully about these middle convolutions. And what was important about these things I was convolving is each of these things were rank 1 invertible sheaves. And you can't build dihedrals from rank 1 invertible things, so to speak, right? Like everything we did here really used heavily the fact that my group mu r was abelian. So I think it would be very interesting to think about the techniques. I think one would also probably have to have some enhancement of the theory of middle convolution, or maybe some substitute for it, to really try to understand what's happening for what I guess I would say are the non-abelian representations of the dihedral group.